Very last class period, we were introducing chapter 10, which was over radicals. And we started talking about the different steps that were associated with radical chemistry. That first step was initiation, and we were looking at the chlorination of methane to form dichloromethane. And your first step was the homolytic cleavage of chlorine gas to form two chlorine radicals. This is the initiation step. So we had looked at what came next, and we had started to talk about propagation. Propagation is the next step when the radical begins to react with other non-radical species. And we went through a series of different types of propagation that were common radical mechanisms or common radical reactions that took place, and we listed all those on the board. Here's just a few of those that we had discussed. Remember that when you have propagation, you're always going to form a new radical, okay? So you're propagating the formation of a new radical. You're always going to have three arrows associated with the movement of a radical, always. Okay? At least in the propagation step. In the propagation step, you will always have three arrows. Initiation and termination, you'll only have two arrows associated with those. All right, so let's go back to the chlorination of methane. How can we initiate the homolytic cleavage of chlorine gas? How can we initiate that? What did we say? How can we get that to start? I'll give you a hint. The formation of radicals actually happens in fires too. Okay, so heat. Yeah. Heat or light. Okay, so UV light or heat can propagate the formation of radicals. As a matter of fact, fluorocarbons, hydrofluorocarbons, chlorofluorocarbons, CFCs, HFCs, these were actually used to fight fires. They're called halon gases. And they were used to snuff out oxygen, and they would produce radicals, which then would terminate radicals formed in the fire and help put out the fire. It's kind of really very interesting way of doing it. And they're still used today. They're no longer in production due to ozone depleting protocols, Montreal Protocol. But there's still a huge stockpile of these. They are still used in the electronics industries. They're used on airplanes and things like that. I think even race cars sometimes have halon fire extinguishers associated with those. So you get your homolytic cleavage, and now you have these two radicals. What happens next? What happens next is propagation. So you're going to have initiation first, and now propagation to start making some new radicals. And how's this going to look? What's this going to look? Jackie?
You have the chlorine with the single-headed arrow, and then you also have the CH bond with the radical, and I think the other part of the CH bond is going in, because didn't you say that the CH4 would be the new radical?
Okay, so the new radical must be on this, right? So the first formation, most of you got this. Most of you got these first two arrows to give HCl as the byproduct, but you didn't know really what to do with the other electron. And the other electron is really just going to stay on carbon. And so that's your next propagation step.
Doesn't that become the new radical because we talked about it was more stable because it had more branches or whatever?
Okay. So in terms of our overall stability, we said that this one was really not that stable, right? And that was just our comparison when we were comparing this one to the other types of radicals that can form. But this is the only other one that we have available to us in this reaction to form. So now I want you to predict, how are you going to get from here to dichloromethane? Okay, so go ahead and talk through that and try and work through that. So you're going to have other steps along the way, and then you should ask yourself, why would this stop? Why would this stop, or will it stop? Go ahead and do that now. Okay, so it is possible, yeah, it is possible to have multiple propagation and multiple termination steps. Yeah, absolutely. Yeah.
How does isn't the radical supposed to clear themselves up eventually? Like imagine we're in the real world. But if you just have solution of a bunch of methane and a bunch of chlorine, how does that end? Because it could just keep initiating and propagating over and over again. So how does it stop itself?
When things run out. When things run out. So go ahead and keep trying. And think on that line, Jackie. Think about what you just said and try and put it to the mechanism. Remember, my question is why would it want to stop? And if so, prove it and see what that looks like mechanistically. Ben, what do you think the next step is going to be?
From there?
Mm-hmm.
Well, I think the second chlorine is now bonded to the H. The chlorine radical is going to bond to that. And the HCl is going to break apart.
Okay.
And it's going to, and that chlorine radical, no,
Isn't HCl your byproduct?
Yeah.
right, so we need an HCl.
Right, Riley, what do you think?
I think that the other chlorine radical would bond to the radical on the carbon, and then you would have another cleavage of chlorines where it takes another hydrogen off.
Okay, so you can have a termination event, right? On the other chlorine radical. Okay. So there you have first chlorine on. And then she says, let's just do this all over again and take this to propagate a new radical. What has to happen?
Another cleavage.
Yeah, you have to have more chlorine gas that gets cleaved. So if you're in the presence of excess chlorine gas, you're always going to have these chlorine radicals around, right? So if you still have more chlorine radicals around, just do it again.
Is coupling and termination interchangeable words?
It is, yeah. So coupling and termination would be the same. Yep. Okay, so now you have your next radical that forms. And your next mole of HCl. And then now what? And then another termination event. Good. Yeah. And then this is going to give you your dichloromethane.
What was confusing me is why we can't get trichlor.
Oh. Can you?
Yeah.
Yeah, you can. Can you get carbon tetrachloride? You can. So the practicality of slowing this down to get these mono, di, tri, and tetrachlorinated products is not actually quite that practical. Okay, so your selectivity is actually pretty challenging when it comes to chlorination. Okay, that actually is the case for most chlorinations that occur radically. Okay, so chlorination is actually really not that selective. It is extremely reactive when you talk about fluorination. fluorine, using fluorine gas, is really highly exothermic, and it is a very fast reaction, and it's not very practical, okay? So you don't see radical catalyzed fluorinations in the literature. It's just not very practical, okay? Chlorination is a little more practical, but bromination is even more practical from a thermodynamic standpoint. So let's take a look at some of that. So there's the first hydrogen abstraction to form that radical, and then the termination at the very event here at the end to show you the first monochlorinated product. So other couplings can occur too. Take a look at this. So you don't necessarily have to have a termination event that occurs with the chlorine. You could have a termination event to form ethane. So you could have two of these that terminate one another to form a whole different product. Okay, so there's other things that can happen within the reaction, and that should be pretty self-explanatory because isn't this pretty reactive, right? And so if there's another one of these hanging around, why would it not want to just grab a hold of it, right? So there are other types of termination products that can form in these processes. Okay. So again, propagation is something that continues to occur as long as there's other radicals around, as long as there are substrates that can be chewed up that are neutral. So remember, propagation is a neutral substrate plus a radical, right? To form a new radical and something else, okay? So you're always propagating new radicals whenever you have a neutral species still hanging around. And there it is. It is difficult to control, and therefore if you have chlorine still hanging around, you're gonna eventually get to carbon tetrachloride. Now, they're saying if you use excess methane, then you can get some of these products, okay? You can control the selectivity slightly using kind of a Le Chatelier's principle approach where you're swamping it with excess reactant or depleting the chlorine gas as a result, okay? Does that make sense? All right. Take a look at some thermodynamics associated with these radical initiators. So you can get peroxides, and peroxides will do a very similar type of thing. I've never experienced use of acyl peroxides before. I have experienced use of these, and they are quite effective. Oxygen, however, is the opposite. If you have oxygen around, oxygen tends to be a killer of these. Same way with quinone. Quinone's another one, and I'll show you. I think there's a slide on that as to how it actually scavenges radicals. But oxygen is a radical scavenger, and so are other molecules like quinone. I'll show you those in just a little bit. Does anybody have any questions on this?
I have a question on the slide before.
Yep.
So, is there any sequence to how the chlorine attaches to the carbon, or does it
No.
just randomly?
No.
So there's no like negative.
Yep. No straightforward sequence. No. Whatever's hanging around in the reaction, it's just gonna get chewed up. Yep. How's everybody feel about the mechanisms? You feel pretty good about those? They're not that hard.
Not naming each part, but
What's that?
I still have to memorize all the names.
Oh, yeah,
of each one.
absolutely. Initiation, propagation, termination, yep,
But
and what they represent. Yeah, absolutely. There it is. Okay. So oxygen being a diradical, hydroquinone will turn into quinone. That's actually a colorful reaction. When you form quinone, it's actually a kind of a royal blue color. Due to hyperconjugation, I've actually formed it before accidentally. The types of reactions, anytime you're running a radical reaction, you do have to purge oxygen out with argon or with nitrogen gas or something like that, so that you can make certain that you're not scavenging any of those radicals using oxygen. So they are considered inhibitors, and I'll show you why. So let's look at hydroquinone. So hydroquinone, you get this hydrogen abstraction, and then you get this resonance stabilized radical. And that resonance stabilization is why it's a great scavenger. Okay? And it occurs, and it can occur twice, which is why it's really actually very nice. And when you end up doing it twice, you can end up forming benzoquinone, and that benzoquinone is the colored species that I was just telling you about. It's like a royal blue. Not that stable of a system. It is sensitive to light, and again, the whole thing is still sensitive to oxygen as well. Does anyone have any questions on that?
Is radicals why you have to like store specific chemicals out of light and like?
Yeah, because you can end up, well, not only forming radicals, but just a general type of breakdown. I mean, that can happen as a result. But you see so many chemicals stored in amber bottles, right? Yeah, it's good. We're not going to go into great detail on this, but I do want to show you some numbers associated with halogenation. And take a look. Look at fluorination. Look at delta H. Negative 431 kilojoules per mole. But what's interesting, when you get all the way down to iodine, look. It's endergonic, it's endothermic once you get all the way down to iodination. So iodination actually isn't that practical either, which is possibly a good little research project to do, where you could do electrochemistry or something to try and promote iodination by adding energy to it, to see if you could iodinate various compounds. I talked to Dr. Eason about that yesterday, as a matter of fact. So only halogenation with chlorine and bromine gas are particularly practical and useful. And let's go down to selectivity and start looking at this. Bromination is much slower, and that should make sense to you. If something is more slower, what's it going to allow for? Control. Okay, that's right. Okay, so the reason why you get more selectivity with bromination is because you can get radicals that can rearrange themselves to make them more stable in the time scale that the bromination is occurring. Okay? Does that make sense? I'll show you a mechanism in just a minute. Let's take a look at the chlorination of propane. Okay? So again, chlorination being less selective because it occurs faster. on that previous slide, that activation energy, look how low it is in that first hump for chlorination. See that? Okay, versus bromination. Look at the products. This one or this one. And what are the radicals that are needed to form those two? And which one's the most stable radical? Taylor? Which one's the most stable radical to form each one of these? Okay. Taylor, what's this one gonna be? Yeah, you do. Where's that chlorine attached?
The primary.
Yeah, so primary. Yeah. And which one of these is the most stable?
The first one.
The first one. That's right. Okay, so the secondary is the one that's the most stable. So naturally, you should think that this one is going to be the major product. Okay, as a result of this one being more stable. But chlorination happens so quickly that this one can still hang around before rearranging itself to the secondary position, and therefore this one should actually still be a contributor in this reaction, in this process. And there it is. So you get about a 60-40 mix, okay, of that particular mixture. Okay? And the only reason you do is because of that low activation energy and how fast the reaction actually happens. So it doesn't have time to completely rearrange to this in the time scale that the chlorination is going to occur. Riley's first.
How do they determine that it's a 60-40 mix?
NMR.
Okay.
Yep. Yep.
How does it rearrange? Can you show us that process?
Yeah. Yeah. Oh, you guys try it. Yeah. You guys do the rearranging. I'm not gonna show you. You guys figure it out. It's not that hard. You guys can do it. I would say there's probably a couple different ways it can rearrange. One would probably be faster than the other. Mm-hmm. That's the first one I thought of, yep. Ruth, think about what's on that other carbon that you drew your arrow to. What needs to go to the other end? What do you think, Hunter? This one, yeah. How do you get this one to here? What's on this carbon? Think about it. What's on this carbon has got to get to the other end.
Okay.
What do you think, Alex? No, you're gonna rearrange this one. You're gonna try and rearrange this one.
Okay.
Try try and rearrange this one to get to this one. Now, Riley, you got an answer? Yeah. Yeah, I think that that's probably good. We give some of you a little bit more time. Some of you were confused about the question. You're gonna learn some new reactions probably today, maybe. Yeah, we may have time to get to those. Some cool transformations. Okay. What's on this carbon that's necessary to get to the other end? Yeah, Alex, hydrogen. Yep. So you got to do some type of a hydrogen abstraction, right? So this would be indicative of the 1,2 hydride shift, right? Kind of the same thing except a radical catalyzed version of that. So now the extra hydrogen is down here on this end, and then you're here with that one hydrogen still left on there, right? So now you've gone from here to here. The slide tells you hydrogen abstraction from a secondary carbon is faster than for a primary carbon, and therefore your selectivity is as such. But look at bromination. Look at that. It's got great selectivity. Okay? It's a lot more regioselective. What is regioselective? Which region of the molecule, is more selective for the experiment, or for the substitution to take place. And this is all based on the Hammond postulate that we just looked at earlier. Okay.
Why is bromination so much slower?
I would say it's probably due to its atomic radii. It's probably due to the electrons are a little more delocalized around bromine. That's probably why it is. It's a little bit larger and bulkier, and the electrons are more spread out, and they're not. You think about fluorine. Fluorine has a small atomic radii, and therefore it's more of a hard anion, right? And then its electrons are not as delocalized. So I have a feeling that that's exactly why bromine is kind of right there. Versus the iodine, its atomic radii is even larger, and electrons are even more delocalized, and that's probably why it's not energetically favorable, because of the reactivity is less. It's so less as a result of that. Yep. Okay. A Hammond postulate. A Hammond postulate is something that I didn't really learn until graduate school. This is quite interesting. I don't know, did you do Hammond postulates in Gen Chem? No? Okay. Hammond postulates deal with potential energy and transition states. And so looking at transition states and where transition states are located allows us to predict not only selectivity, but it allows us to predict products as well. And what they've determined through just examining this is that where the transition is located, if it's located closer to the product side or closer in energy to the reactant side, helps you understand not only the mechanism, but it also helps you determine and look at the selectivity of the reaction as well, okay? And so, I probably will not be testing you on Hammond postulates right now, but maybe later in the semester, as time goes on. You've seen these already. I mean, you saw these with SN1 and SN2 reactions, right? Whereas SN1, you have two transition states, right? And here is the carbocation intermediate, okay? So you've got transition state 1, transition state prime, okay, or 1 or 2, whatever. And the Hammond postulate reveals that you have not just two transition states, but also an intermediate. Whereas the SN2 reaction, you did not have a carbocation, you just had one transition state in the SN2 reaction, okay? Because it's only a one-step reaction, and then the SN1 reaction was a two-step reaction, okay? So those were also Hammond postulates that we were looking at last semester. So they're showing you a little bit more about that transition state and what that looks like. And essentially the internuclear distances, and bond breaking and bond making, and where those are specifically located. Let's take a look at this guy. You still see the selectivity, right? Still follows the same pattern for chlorinating or brominating a tertiary system. Okay? Selectivity is a little bit better, 65-35, right? Because it was 60-40, remember? And that again comes back to the stability of that tertiary radical. Let's look at, we have enough time? Yeah, we have enough time. Let's look at a new reaction.
Will you only have rearrangement of these hydrogens that are attached to the
Typically, yeah. I think that there are probably other systems that can undergo rearrangement. We just haven't seen those yet. But that's a good question. Yeah. Predict products that could form from this. Predict the products that could form from this. Talk it out with someone next to you if you need to. As we continue to progress through this semester, I'm going to start feeding you some research papers out of the literature based upon what chapters we're in. I'll show you some I'll show you some synthetic organic chemistry literature examples of radical catalyzed reactions and radical catalyzed halogenations that have been used to make larger molecules or larger small molecules, and why they're useful, why they're practical. You guys will be able to see some different varieties. I'll pull some research papers for you to take a look at. Okay, drawing upon last semester, if any of you remember, there is a reaction up here that might actually occur. What might it be? Oh, yeah, what's that thing called?
I always just called it bromine cyclic bridge.
The bromine cyclic bridge, the,
Which is wrong,
the
but-
bromonium cation, right? So, remember, this guy, right? Bromine negative coming in, kicking this off. So the possibility look at me drawing a 6-membered ring here. A dibrominate species, right? Possibility of having something like that form? Is that possible, you think? Yeah, if you got bromine hanging around, that is a possibility, okay? What's gonna be your most stable radical from this species if you do get initiation and propagation? What's gonna be your most stable radical from this one? What do you think?
Could you have the radical right there where you're holding it?
Right here? Okay, so get rid of the double bond and put it here maybe?
Yeah, but could the bromine, the radical of bromine go to the lower carbon?
Okay, so then maybe have something like that.
And then couldn't the other one just make another carbon bromine bond?
But then you're back to here. Right.
So we don't want that.
The hydrogen.
But I mean, let's just consider this, right? Let's just consider this. Would there be any selectivity? Probably not. Okay, so you're quite likely could end up not only with the trans or anti, but also the cis, right? So you get this other mixture of products.
Could you use the carbocation range and get like a dibromine with different ozone carbons?
Oh, okay, where this could rearrange, and then you could get a bromine over here. Okay, sure, yeah. How might you be able to look at this? Actually, I'm gonna come back to this. Give me another stable radical, a more stable radical than the one that you predicted, the one that you thought about. This one.
If the hydrogen came off, but the thing with the double bond, hydrogen station.
Okay, so this one is actually less stable. This one is actually called a vinyl radical, okay? Vinyl radicals are actually not that stable. They're not stabilized by resonance, okay? It would be similar to a vinyl carbocation. Be similar to that, okay, which is not that stable. So if that one is not that stable, where do you want to put the radical at? Oh, adjacent to the double bond. Here. And there it is. That's the allylic radical that we talked about on Monday. Okay, so allylic radical would be more stable, and therefore you might predict what product? What product might you predict? Bromine on top, bromine on top here, plus HBr. And when we get back on Friday, I'll show you that there's a different reagent that you can actually use instead of bromine that will actually give you a bromine radical, but will prevent the side products that we just discussed from forming in the reaction. Okay, it'll give you a little bit more selectivity, and we'll discuss that reagent on Friday.
Will that be a quiz on Friday?
There will be a quiz on Friday.
Just over chapter 10?
No, probably we'll have maybe another NMR type problem in there with some of the stuff from the beginning of chapter 10. Yeah. So you may see another multi-conceptual problem. Now, mass spec, IR, NMR, yep. We'll see you on Friday. No, tomorrow for lab.
Yeah, we
Can't write you off that easily.
can't skip into knowing.